The skeletal system is the supporting framework for the soft tissues of the body. The skeletal system is undergoing continuous rebuilding and remodeling, and it is considered to be a living organ system. It's comprised of the bones, as well as cartilage, ligaments, and other connective tissue, all that help stabilize or connect bones. And so the main function for bones is to support our weight and interact with our muscles to produce precisely controlled movements. Another vital role is that bones also serve as a reservoir for calcium and for phosphorus. Cartilage is weaker than bone, however, it is more flexible and resilient. There are three main functions of cartilage. The first is for supporting soft tissue, and we have three different types of cartilage that we find throughout the body that we'll cover a little bit later. The second is that we have a gliding surface found at the joints or at the articulation points where we have two bones that meet, so this prevents from having lots of friction. And thirdly, cartilage acts as a model for the formation of bones in the body. And so this stems early on at early embryonic development, where we all start as cartilage and then convert to bone once we have enough calcium and phosphorus. The mature cells of cartilage are called chondrocytes. And so these chondrocytes are scattered throughout the matrix, where they're found within the ground substance and the protein fibers. The chondrocytes are specifically in these special spaces called lacunae, and they mature from chondroblasts, which are going to be the immature cartilage cells, or the stem cells of cartilage. And so one of the functions of chondrocytes is that it maintains the matrix, and it helps to maintain a healthy and viable matrix for the cartilage. If you remember, cartilage is avascular, meaning that it does not have blood vessels or nerves as well, and so nutrients have to diffuse through the matrix. The perichondrium is going to be a special area where we have growth that occurs on the outside edge or the periphery of cartilage. And so when stem cells at the internal edge of the pericardium begin to divide, this is where we get formation of new chondrocytes, which mature from chondroblasts. There are three main types of cartilage that we have. The first is hyaline cartilage, and this is the cartilage that's predominant during embryonic development before it converts to bone. And the interesting factor that we have with this is that there is more ground substance instead of protein fibers throughout the connective tissue. And so we find hyaline cartilage as adults between articulation points of two bones, so at joints. Also, we find hyaline cartilage at the bridge of our nose, and it is the cartilage that we find that connects our ribs to our sternum. And also, there are amounts of hyaline cartilage with our trachea and our larynx. The second type of cartilage is elastic cartilage, and this is comprised of elastic fibers, and so this tends to be very flexible, and it has less ground substance than hyaline cartilage. And so because of the elastic fibers, that's why we're able to bend our outer ear and in multiple directions. We also find elastic cartilage within our epiglottis, which moves up and down as we ingest food. And then the third and strongest type of cartilage is fibrocartilage. And this can withstand the heaviest pressures and absorb the most shock of the three types of cartilage. And so we find fibrocartilage in between the vertebrae, as well as our pubic symphysis, which connects our os coxae of our pelvic bones. And then these comprise our menisci of our knees. Fibrocartilage will have more protein fibers than ground substance, and predominantly they will be our collagen fibers. And so here are examples of where you can find each of the types of cartilage. So bones are living organs, and so because it is an organ, it contains all four tissue types. And so some of the primary factors that we see are the connective tissue proper, which comprises the periosteum, which is going to be the perimeter of the bone. We have cartilage connective tissue, which is found at the ends of bones, and this is where we get the articular cartilage, so prevents friction from bone-to-bone contact. We have smooth muscle tissue that forms the walls of blood vessels that supply the bone, and then so we get formation of bones within the bone marrow. We have fluid connective tissue, and so this is where we have bone that is produced within the bone marrow. We have epithelial tissue that lines the inside opening of blood vessels, and then we also have nervous tissue where nerves supply the bone. The functions of bone include the support and protection for the framework of the entire body. So bones are responsible for protecting delicate tissues and organs from traumatic injuries, and such examples include the rib cage protecting the heart, the cranium protecting the brain, the vertebrae protecting the spinal cord, and then the pelvis protecting the digestive, urinary, and reproductive organs. Bones and bone tissue also serve as attachment sites for skeletal muscle, soft tissues, or other organs. And so the bones function as levers when skeletal muscles contract. And so because of that, then that can alter the direction and magnitude of the forces that are produced by skeletal muscle. Another function of bone and bone tissue is hemopoiesis, which is the formation of blood. And so blood cells are produced in the red bone marrow, which interestingly, as adults, we only have red bone marrow within the axial skeleton, which include the fat bones of the skull, the vertebrae, the ribs, the sternum, and the os coxae, which are the hip bones. Children, on the other hand, have red bone marrow that is found within all spongy bones. And then the final function of bone is the storage of minerals and acts as an energy reserve, where we store more than 90% of calcium and phosphate, which then can be released by degradation of bone. And so calcium is essential for muscle contraction, for blood clotting, as well as conduction of nerves. And phosphate, among various roles, but is important for ATP utilization. And so once the bone connective tissue is broken down, and the minerals can be released into the bloodstream where they are needed. The classification of bone is based on their shape, and so we have 6 main shapes that we examine. The first and most common is the long bones, and these have a greater length than they do width, and these tend to have elongated cylindrical shafts or diaphysis. Within the inside of the diaphysis, we find the medullary cavity, which contains the yellow bone marrow. We find the long bones in our extremities, such as the upper limbs, such as the arm, the forearm, the palm, and our fingers, as well as the lower limb. And so this can be our femur, our leg, sole of the foot, and then our toes. And so the longest bone in our body is a long bone, which is the femur. The second classification shape is the short bone, and so these have a length that is nearly equal to their width. The external surface of these short bones are covered by compact bone, and then the interior is composed of spongy bone. So the examples that we have are the carpals, which are our wrists, and then the tarsals, which are the bones within our foot. A sub-classification, but it is considered to be its own, is the sesamoid bone. And these are going to be tiny seed-shaped bones, and we tend to find these along the tendons of some muscles, and our patella specifically is the largest of the sesamoid bone. Next we have flat bones, and so these are going to have flat, thin surfaces that are going to be comprised roughly parallel surfaces of compact bone, and they have an internal layer of spongy bone. They have these extensive surfaces, which are sites for muscle attachment to protect underlying soft tissues. And so examples that we find flat bones are the roof of the skull, the scapula, and the sternum, as well as the ribs. Special characteristics that are in their own category are sutural bones, and so these are only going to be found within our cranium, and so they are fused along sutures, and so this is where we get our suture lines when bones ossify and fuse together. The last shape is irregular shaped bones, and so these just do not fit any criteria of the previous bones, and so they are very different. They're all complex shapes, and none of them have any similar pattern to them. And so the bones that we find that are classified as irregular are the vertebrae, coxae, which are our hip bones, some bones within our skull, such as the ethmoid, the vomer, and then the sphenoid bone, which would be all considered to be just irregular in shape. General structures of long bones include the diaphysis, which is the shaft of the long bone, and so this is going to be the middle portion of the long bone. And so this tends to be elongated and also cylindrical. The epiphysis is going to be at each end of the long bone. And so these tend to be a little bit knobby in appearance because they are responsible for strengthening the joint and also to provide added surface area for bone-to-bone articulation. Also, this is where we have a lot of attachments of ligaments and tendons, which ligaments are from bone to bone, and tendons are attachments from muscle to bone. And then the third region of a long bone is the metaphysis, and this is where it is a thin region between the diaphysis and the epiphysis. And so this is where we also have the epithelial plate, or the growth plate. The epithelial line is going to be a region, again, found within the metaphysis, and this is where we have a lot of growth that occurs as we are children. And so we have, as children, a thin layer of hyaline cartilage that is within this epithelial line, or epithelial plate, and this allows for growth into the diaphysis region of the long bone. And so once the epithelial plate is closed, we have this line that is a remnant of the epithelial plate and growth and during development. The articular cartilage of long bones is going to be the thin layer of hyaline cartilage that we find covering the epiphysis at the joint surfaces. And so this allows for decrease in friction as well as acts as a shock absorber. The medullary cavity is going to also be known as the marrow cavity, and this is found within the diaphysis, and it is the hollow cylindrical shape that we find there. And as adults, this is where we find the yellow bone marrow, and then as children, this is where we have the red bone marrow. This area lacks bone tissue because it is a hollow cavity. The endosteum is going to be the incomplete layer of cells that covers all the internal surfaces of the bone, such as the medullary cavity. And so this is where we find all the different types of bone cells, including the osteoprogenitor cells, the osteoblasts, and osteoclasts, which are responsible for our immature, mature, as well as degradation cells. And so as we have growth and development and remodeling and repair, we find these cells are found and housed within the endosteum. The periosteum of the long bone is going to cover the outer surface of the bone. And so one way to associate periosteum is think of it as the perimeter of the bone. So it serves as the outside of the bone. And so this is going to be a tough sheet that is formed of dense, irregular connective tissue. Now we don't find the periosteum, though, by the articular cartilage, because that is special to where the joints, where two bones meet. The periosteum protects the bone from surrounding structures. It anchors the blood vessels and nerves to the surface of the bone, and then also provides stem cells for bone growth and for fracture repair. The special features that anchors the bone to the collagen fibers are called the perforating or the Charpet's fibers. And so here in this image, you find these little fibers that are associated with the periosteum. There are four main types of cells that we find within bone connective tissue. The first are osteoprogenitor cells, and these are going to be the stem cells that are derived from the mesenchyme. When they divide, they produce another stem cell, or osteoprogenitor cell, and then another committed cell that becomes an osteoblast. And so we find osteoprogenitor cells within both the periosteum and the endosteum. The second type of cell that we have are the osteoblasts, and these are formed from osteoprogenitor stem cells. They form the bone matrix, which then later calcifies and hardens as a result of the calcium salt deposits. Osteoblasts are responsible for formation of new bone, and osteoblasts become entrapped within the matrix that they produce and secrete, which then they differentiate to become osteocytes. Osteocytes are going to be the mature bone cells that again are trapped within the matrix that they secreted as osteoblasts. They live in small spaces within the matrix, again called the lacunae, and they maintain the bone matrix and detect mechanical stresses within bone. Osteoclasts are going to be large, and they'll have many nuclei, and they also are going to be phagocytic. They are derived from fused bone marrow, and due to their size, they have an increase in surface area that allows them to be involved in bone reabsorption. So they secrete hydrochloric acid that dissolves mineral parts which are, again, calcium and phosphate of the bone matrix. Lysosomes within these osteoclasts are going to digest and degrade and then dissolve the organic matter of the matrix, so then that will be expelled out of the bone cells. Once this occurs, then the calcium and the phosphate ions are released into the tissue fluid, and then so that they can travel to the blood, where then the blood can carry calcium and phosphate wherever it needs. So there's a delicate balance that occurs between osteoclasts removing old matrix and then osteoblasts creating new matrix. The two types of bone connective tissue that we have are compact bone, which is also known as dense or cortical bone, and spongy bone, which is also known as trabecular bone or cancellous bone. Compact bone is solid and it is relatively dense compared to spongy bone that is more porous and acts similar to a sponge. Compact bone also forms the solid external walls of the bone, whereas spongy bone is located internally, primarily within the epiphysis of bones. The unit of bone is the osteon or the Haversian system. Osteons run parallel to the diaphysis of the long bone, and they tend to be cylindrical in shape. The central canal, or the Haversian canal, is a cylindrical channel that lies in the center of the osteon, and this is where we find blood vessels and nerves that supply the bone. The concentric lamellae, which lamina stands for a plate, these are going to be the rings of bone connective tissue that surround the central canal and then make up most of the osteon. Each lamella has collagen fibers that are oriented in certain directions. And so you can have one lamellae that is going to have the collagen fibers that have the direction that is superior and to the right, and then the adjacent lamellae will have collagen fibers that are going to be in the direction of superior and to the left. And so this alternating pattern of collagen fibers gives bone part of its strength and resilience. The osteocytes, again, are going to be the mature bone cells, and these are going to be found within the lacunae between adjacent concentric lamellae. The canaliculi are going to be these interconnecting channels within bone, and they provide the nutrients, minerals, gases, and waste that travel through passageways between the central canal and all the different osteocytes. And the Volkmann canals, or the perforating canals, also contain blood vessels and nerves. However, they run at perpendicular angles to the central canals and help connect the central canals so that there is a continuous vascular and nerve innervation connection among the different osteons. The circumferential lamellae are going to be rings of bone that are going to either be in an external circumferential or they will be in an internal circumferential lamellae. And so the ones that are going to be the external circumferential lamellae are going to be just internal to the periosteum of the bone, and then the internal circumferential lamellae will be internal to the endostenum. The circumferential lamellae will run the entire circumference of the bone itself. However, as a reminder, the blood vessels and nerves run through the Haversian and the Volkmann canals. An additional special feature for spongy bone is going to be this open lattice of narrow plates of bone, and we term this trabeculae. The trabeculae are going to be composed of parallel lamellae And this is where we have osteocytes, where they rest in the lacunae, similar to compact bone, and also have numerous canaliculi from the lacunae. And so nutrients reach the osteocytes by diffusion throughout the caniculi that open up to the surface of the trabeculae. The trabeculae often has this meshwork of crisscrossing, and this crisscrossing appearance helps to increase resistance to stresses that are applied in many different directions, and thus helps the overall stress that the bone can have placed on it. Short, irregular, and flat bones do not contain special regions of the diaphysis, epiphysis, or the mural cavity. However, with flat bones, there is one particular region that we find, and this is called the dipole. And this is where we have a layer of spongy bone that is going to be sandwiched between two layers of compact bone. And we find this within the bones of the skull. We have hormones that are responsible for controlling and regulating the growth patterns in our bone, and then they also alter the rates of osteoblast and osteoclast activity. And so the first hormone is growth hormone, or also known as somatotropin, and this is going to be produced by the anterior pituitary gland, where it stimulates the formation of a second hormone called somatomedin, which is produced by the liver. This somatomedin is responsible for stimulating growth of cartilage in the epithelial plate. Thyroid hormone is going to be secreted by the thyroid gland and stimulates bone growth by influencing the basal metabolic rate of bone. And so we need to have a balanced ratio of growth hormone and thyroid hormone until we hit puberty, because they're responsible for maintaining the epithelial plate. And so if children have too low of either growth hormone or thyroid hormone, then this will result in children and adults with shorter stature. A third hormone is calcitonin, and this is secreted by the thyroid gland, and this secretion is in response to higher levels of calcium within the blood. This calcitonin then will encourage calcium deposits from the blood into bone, and thus inhibit osteoclast activity. And if you remember, osteoclasts are the ones responsible for phagocytizing and releasing calcium into the blood. So if we have high levels of calcitonin, this results in high levels of calcium being brought from the blood to the bone, and so there doesn't have to be this degradation problem of the osteoclast activity. A fourth hormone, parathyroid hormone, is secreted by the parathyroid glands, which are close to our thyroid gland and found on the back, and there are 4 of them. And they are secreted when they have decreased levels of calcium in the blood. So the opposite effect of calcitonin. And so parathyroid hormone will increase blood calcium levels so that other body tissues can use calcium. And so in contrast to calcitonin, this will increase osteoclasts to reabsorb bone, and thus increasing calcium levels that will then be released into the bloodstream. Lastly, our sex hormones of estrogen and testosterone are going to be secreted once we hit puberty, and these will be responsible for increasing the rate of bone formation by osteoblasts in the ossification centers within the epithelial plate. And so basically, these hormones are responsible for increasing the length of bone and also to increase their height. When we hit puberty and have increased levels of estrogen and testosterone, this marks the end of growth at the epithelial plate. where we have more bone that is produced at the epithelial plate than cartilage, and so this excess growth of bone will tend to get rid of the epithelial line. So we have three main vitamins that are important for maintaining and growth of bones. And so the first one is vitamin A, and this is important for activation of osteoblasts. And osteoblasts, again, if you recall, are going to be our stem cells that will then develop into osteocytes, which are our mature bone cells. Vitamin C is also required for normal synthesis of collagen, and so a lot of sailors back in the day who did not have enough vitamin C from fruits and vegetables tended to have a lot of scurvy, and this did not allow for collagen to be produced, and so they would have weaker bones. And so usually this would be seen actually within their teeth. And then finally, vitamin D is important for stimulating absorption and transport of calcium and phosphate ions to the blood. And so we also need vitamin D for calcification of bone, where when we have high levels of calcium and phosphate, we have an increased secretion of calcitonin, which then encourages the deposit of these minerals into our bones. And so problems with deficiencies with vitamin D occur with rickets, where the digestive tract is unable to absorb calcium and phosphorus and does not lead to then the formation of bone. Mechanical stress, such as the stress that we see with skeletal muscle contraction and gravitational forces, are important for normal bone remodeling. And so this helps to increase the strength over a period of time by increasing the amounts of mineral salts like calcium and phosphorus that are deposited, and also for collagen fibers to be synthesized. The increased levels of exercise also helps to increase the levels of calcitonin, which again, our calcitonin is responsible for inhibiting bone reabsorption by osteoclasts, and also encourages bone deposits by osteoblasts. Athletes tend to have a thicker bone mass because of the repetitive and stressful exercises that they're subject to. So weightlifting and walking help to build and retain bone mass, whereas those that are subject to bed rest or that have a fracture and are in a cast, or even with space flight, we see that due to this lack of mechanical stress, the bones weaken because of demineralization, so they're losing these minerals within the bone matrix, and also they have a decrease in the amount of collagen that is being formed. So research has found that total bone mass in young children and in young adults can provide a decrease later in life for the inevitable loss in bone mass that we see with aging. And so 70 and 80-year-olds who perform some type of moderate weight training have been found to actually increase their bone mass. And so this is a reversible age-associated change that we can increase bone density with exercise. Sometimes we have our bones that break even though our bones have great strength. And this is usually due to some type of different stress or sudden impact. And when our bones break, this is called a fracture. And there are three main causes of fracture that it can occur. They are stress, trauma, and pathology. Stress fractures are due to thin breaks that are caused by increased physical activity levels, where our bones are subject to repetitive loads. And so this is often seen with marathon runners and long distance runners. Also, we have traumatic fractures, and this is due to impacts or excess stress in the bone, And then finally we have pathologic fractures, which are due to some type of disease. And so this is often seen with osteoporosis and when we have fractures within the vertebrae. Now the types of bone fractures that we commonly observe are simple fracture, and this is where the bone that is broken does not penetrate the skin and it remains internally. The second type is compound fracture, and this is where we have one or both ends of the broken bone that is able to pierce through the skin and the underlying body tissues, including muscle. And the third type is comminuted fractures, and so this is where the bone is splintered into many pieces that are small pieces between the main parts of bone. Compression fractures occur when the bone is squashed, and so this may occur in a vertebrae during a fall. Depressed fractures occur when we have broken parts of the bone that form a concavity or is depressed inward, and so this can result within the skull fracture. The spiral fracture is going to fracture spirals around an axis of a long bone, resulting from some type of twisting stress. Green stick fractures are going to be considered as partial fractures, with the convex side of bone breaks and the other side is bent. And so these are considered to be incomplete breaks and are often found in children. Hairline fractures are going to be fine cracks in which sections of the bone remain aligned. And so this is very common in the skull as well as with long bones too. And so here's an X-ray image of a spiral fracture that has occurred within the femur, and this was a result of some twisting motion where this person had to have several rods placed to help realign that femur. Here in the green stick fracture, again, this is going to be a partial fracture where it's an incomplete fracture within. This is the radius of the arm. Following a fracture, healing can vary in the duration for how much it occurs. So for instance, healing within a simple fracture can take about 2 to 3 months, whereas a compound fracture could take much longer. In general, kids tend to heal quicker than the elderly, and as we continue to age, the healing process of bone fractures tends to increase with time. So the stages of bone fracture repair include, first, once a bone fracture occurs, then what happens is that this tears blood vessels inside the bone throughout the different canals and within the periosteum. This causes bleeding, and then we have a fracture hematoma that occurs from the clotted blood. The second stage that we have is that the regenerated blood capillaries now are able to infiltrate the fracture hematoma because we have an increase in osteoblast activity in both the periosteum and the endosteum surrounding the fracture site. What needs to happen first, though, is that the fracture hematoma must be recognized to actively grow connective tissue, and this is called a procallus. Fibroblasts within the procallus can produce collagen that helps to connect the broken bones together. Chondroblasts, which are going to be the stem cells of cartilage, can help to grow connective tissue and then to form the dense regular connective tissue that's associated with that cartilage. The procallus eventually becomes a fibrocartilaginous or a soft callus. And this stage lasts typically for about 3 weeks. The third stage is now the formation of a hard or a bony callus. And then so within a week after the formation of the soft callus, we have osteoprogenitor cells in the areas that are adjacent to the soft callus, which become osteoblasts and produce the trabeculae of primary bone. The soft callus is then replaced by bone, which forms this hard or bony callus. The trabeculae of the hard callus continues to grow and then thickens for several months after a fracture occurs. Then the last stage is the bone now being remodeled, and this hard callus can last for about 3 weeks to 4 months, as we have various amounts of osteoclasts that are removing excess bony material from the exterior and interior surface of the bone. Compact bone replaces primary bone, and so the fractures usually leave a slight thickening of the bone. However, this is not always the case with every instance. And so after a fracture, due to the amount of osteoclasts that are found now, and osteocytes that are there, can actually have thicker bones as compared to before the fracture, once it's completely finished healing. And so here's a picture of the 4 different stages, where at the top left we have the hematoma forming, which is going to be a large blood clot. Then we'll have the response of the soft callus forming. That soft callus then will turn into that cartilaginous-like callus to then now this hard bony callus. And so finally we have the bone that is completely remodeled. And so in general, projections are going to be responsible for difference in, or allowing for muscle attachment sites. And also this is where we'll have sites of articulation of multiple bones. When we have depressions and openings, these are going to be responsible for the passage of blood vessels or the passage of nerves through the bone. And so these bones and nerves and blood vessels will tend to be larger in size. Also, these depressions and openings may be responsible for articulation sites between various bones. And so these are the terms that you should become familiar with, where we have the 4 different types for articulating surfaces. So we have condyles, facets, heads, and trochleas. We have depressions, which we find the alveolus or alveoli for more than one, fossa or fossae for more than one, and the sulcus. For projection sites, we have the crest, epicondyles, lines, processes, the ramus or rami if there are more, spine, trochanter, tubercle, and tuberosity. And then the openings and spaces are for, we term them as canal, fissure, foramen or foramina for multiple, and sinus. And so you'll see these throughout many bones. However, every bone will not have all of these terms in them. The more familiar you are with these basic and general anatomical terms, the better off you will be in understanding the basic structure for each bone. With aging, we find that we tend to lose tensile strength of bone that is decreased due to a decreased rate of protein synthesis. That decreases the ability to produce organic portion of the bone matrix, and thus increasing the inorganic materials of the bone matrix. And so this increase in inorganic material results in the skeleton being more brittle and susceptible to breaks or fractures. And so also we tend to lose calcium within bone and other minerals, which is termed as demineralization. again resulting in thinner and weaker bones due to insufficient ossification. And so this is termed as osteopenia. And so as we all age, we become osteopenic because of this reduction in bone mass. This can start as early as 35 to 40 years of age when we see declines in osteoblast activity, whereas osteoclast activity might stay the same as before. And so the rate of breaking down bone is faster than the building and growth of bone. And so with each decade of our lives, women tend to lose more skeletal mass than men, especially after women hit menopause, due to the changes of hormone levels of estrogen. So common areas that we see that are affected by osteopenia are the vertebrae, our jawbones, and the epiphysis tend to lose the largest amounts of bone mass. And so this results in a decrease in height, loss of teeth, and then fragile limbs, especially with the femur. A disease that occurs with osteopenia is osteoporosis. And so this is a condition where the bone mass becomes reduced enough to compromise normal functioning, including walking and sitting. And so these people with osteoporosis are even more prone to fractures, where these individuals have both the bone matrix and calcium that are lost, particularly within spongy bone. And so here is a picture. On the left-hand side, we have normal bone, and then osteoporotic bones on the right-hand side. And what you can see is we have more spaces that are larger compared to the normal bone, and so this will prevent bone growth and allow for weaker bones for an individual.